So the R package ESD started off as a package to carry out empirical statistical downscaling, but the empirical statistical downscaling also implies a lot of data handling, processing and pre-processing, and also climate analysis. So and we wanted to make this like a generic tool and also very flexible. So in the end, it ended up as extreme simple data. So and it's meant to make climate analysis much easier and faster for people. So basically, the statistical downscaling and also the idea behind this is to actually have some information and then combine it with some more information, and then you end up with even more information. So it's really quite simple. It's actually trying to bring together different types of information and get a better picture of what is going on. So it's a tool to analyze connections, and empirical statistical downscaling is one of these ways of analyzing these connections and make use of them to make predictions. So it reveals dependencies between different scales, and it captures systematic geographical dependencies. And basically, in empirical statistical downscaling, empirical information is added to model simulations. So this tool was actually also inspired by the Ferret tool made by NOAA, Pacific Marine Environmental Lab in the US, that was made many years ago, and it was actually a model for making simple analysis. So what is empirical statistical downscaling? Local climate depends on the ambient large-scale situation in that area, and basically we want to use this dependency to deduce the consequences of a global climate change in a local, like in a place where you're interested. So here's one example: the annual precipitation in Oslo, and how that is related to the mean sea level pressure over the North Sea. So we use a multiple regression, and you can see here on this figure here, the first panel here shows the sea level pressure anomalies, and there's a low over Scotland, which implies that you have southerly winds for Oslo here. And the next panel is a scatter plot, which shows the cross-validation analysis. So basically, you take parts of the data, you calibrate, and then you use the rest of the data for prediction to tests on independent data, like how well you actually are able to reproduce the observations, and then you do that in different segments and replace different segments with independent data. So the cross correlation here is 0.58. So it's fairly okay. So there's a connection there, but it's not perfect. And the lower panel here shows the observations in black. So these are the annual precipitation amounts, and then the red curve shows the calibrated model. So basically, when you calibrate a model, we did trend the data before because we want to see afterwards if the model is able to capture the slow trends or the slow changes over time. And in this case, you can see that the black dashed line is the observed trend, and the red dashed line is the one with the calibrated. So this mean sea level pressure is not able to capture the trend in the rainfall, and that is probably more is due to thermodynamical aspects like more moisture or changes in the air property rather than the dynamical effects. So this just shows like how we can use the tests and understand what is going on. So ESD is basically now rebranded as extreme simple data, so to make the analysis quicker and simpler for the users. So basically, it's analysis carried out in R, and the R package is available from the GitHub, this address here, metno-esd, and it's like sort of a kitchen sink for numerical analysis. Basically, like you can use regression or even artificial intelligence well, regression might also be viewed as artificial intelligence to some extent. So the principle is that we have the data, and we also make use of the metadata and also the computer code and documentation, and together that's a bundle which which makes the analysis much more robust and also more intelligent. And also what we try to aim for is to actually get the data straight into RStudio, so like to read an SCDF from thredds or OpenDAP, or say ERA5, the reanalysis from the climate data storage, the CDS from Copernicus or station data indices. It also can run scripts in Python and import from Excel. And then you use this package for evaluation and also visualization. So one advantage with the common tools is that people who use the same tool, they can discuss problems and solutions and help each other. And also it provides some kind of quality control. I also like to sort of think of this ESD tool as a sort of like building with Lego, so you can sort of have this sort of same kind of bricks or bits that can be reused in many different ways. And we try to make this sort of tailor-made and user-friendly using the S3 method in R. So plots will actually know how to plot different types of objects, if it's like a station data, or if it's like a field, or if it's an EOF, for instance. The same thing with map and subset and EOF. So subset lets you dissect the data and actually pick out like parts of the data. So these are meant to make life easier, so the user doesn't have to remember a lot of different variations of these functions. So we try to make these functions consistent, and also like with logical arguments, and also have the defaults. And then once you do the analysis, it will actually add like a stamp in the metadata, like with provenance, and also and then you can carry on and do different types of analysis. So like the output from one function can be used as input for the other function. That's sort of like this Lego type of idea. So we can use the ESD package for generating graphics, and here's one example. We use also another package called animation, and do have the code here. So basically you retrieve, so this is an SCDF file with the topography of the reanalysis, and then we create a map was stored in land, and then we set like everything that is below surface is set to 0. And then we just run this video where we map this on a sphere, and also then we vary the longitude like for the view here. So then it's like made for 360 times, and also we have set a style here to night, so you can see that you have the shading on the sides here, and also the new here. So it doesn't is full, so it doesn't make a new window each time, so they will plot on top of each other. And then here you can actually save it as MP4 data, even though this is a GIF, so it's quite different. Also, like here's another example with from ERA5 reanalysis with 10-meter wind, and you have the wind arrows. So basically would fetch the SCDF files from Copernicus, and then you have to read it in, and then you have to plot it. Here's another example showing how you can study connections. So here is the mean sea level pressure from NCEP reanalysis. Here you have sea surface temperatures. Basically you would take a subset. So actually here I've cheated, so it has also read in the sea surface temperatures here as well. And also basically it would subset the sea level pressure, and then we estimate the EOFs of both. So these are basic annual data here, annual mean, and then carry the CCA analysis, and then plot the CCA here. So you can see that here is the sea surface temperatures, and here are this mean sea level pressures. The patterns that are the mostly correlated, so it's correlation 0.78, and here you can see the two together. So this is basically the analysis. So here is the ERA5 reanalysis, and here is our SCDF file with 10-meter wind, and then we have the wind arrows. So basically you have the Here it also here's an example where it reads the radar data from threads from Norway's OpenDAP service. So the idea here is that you just say, okay, I want a radar. I don't need to know exactly where it's stored. So here it reads for 2019. So the IT is index time, and you also have S, which is index space, and you have IP is index pattern and so on. So it's like fairly logical the way you sort of subset or choose these things. So the map produces a map. So by default it will make a mean map, but you can also add as an argument called fun with capital letters, and you can have any type of operation on when you do the mapping. Here's another example. Here we just have the esd package also comes with some example data. Here's some storms example data, and it will actually pick a subset of storms here. So here's the IT like index time. So it you have two different dates. You can also read local sea level series from the internet, so it knows where to find this gloss data here, the tidal data, and here is a map just showing the trend of this data. It can read stations from threads as well. So here you can read the metadata. This is basically provides you a data frame with all the data that is available. It's much quicker to read the metadata than the data itself. And then you can also read the like station data from threads. So it's fairly quick still, but there's so much more data to read from data. So there's one example of some analysis made. So I will just want to show the structure of a typical data set. So here's a sea surface temperature. There's a field. So basically you have time first, and then you have a space dimensions. So the space are combined into one dimension here. So then it basically it will have to the esd package will disentangle that. But the reason why we do that is that we use a zoo object, and that takes care of all the calendars and all the times and so on. It makes life easier for us. So then it's easier for us to actually deal with this space or the disentanglement afterwards in that function. So basically the data is here, and then it comes with some metadata. So this is like a header in an SCDF file. So it's variable name, long name, units, longitudes and latitudes, and whether it's it starts on Greenwich or not when you do the plotting, and also what file it was, time units, and also title of the data. And then you have a history stamp here, and it basically tells you that you retrieve the data, and then you took the annual field, and then you did a subset. And here are timestamps of the when the operations were carried out, and here's a session. So basically it used R version 3.61, and it used ESD version 1.9.16, and also it was done on a Linux station. And there are some more information also stored here. So some of these are key metadata, and some are just extensions, so you can add as much as you like if you really want. And there's also the indices and dimensions. So, but there are some limitations to this esd package. So at the moment we only have two dimensional surfaces, so it's like just flat surfaces, like say surface temperature and or sea level pressure, and one dimension time. We could actually extend this also to have three-dimensional volumes as well, but we haven't actually done that yet. So, and also it works for data sets less than 1 gigabytes on our machines, and you can do the analysis on a laptop if you have a powerful laptop, but you can also do it on supercomputers as well. But using R means that you basically have not as fast processing, but then again you save the time by not having to do all the programming, because you spend much less time doing setting up the analysis, rather than and then if you had to program everything on a supercomputer.